These tests were conducted to demonstrate the effectiveness of Eaves' water system in an ember attack situation. Burning embers from a bushfire are hot, very hot. A simulated roof structure was constructed incorporating valley and external corners with a 30-degree pitch. Prior to conducting the roof test, as step 1, sample embers were extracted from the fire and size and temperature recorded. The fuel was randomly selected from local trees and allowed to burn for approximately 20 minutes. The size selected ranged from 10 to 25 mm in diameter and 10 to 50 mm in length. Surface temperatures were recorded consistently above 250 degrees C. The effect of embers on ASA plastic was conducted as step 2. Eaves' water system used plastic components to connect the enclosed metal profile. AS 3959-2009, page 3, item 16 states, there is no test method available to assess the performance of fire-resisting materials such as plastic. The temperature of embers, similar to those observed in step 1, was recorded, and they were placed directly on the upper surface of Eaves' water system plastic components. The surface temperature of the plastic and the embers was monitored and recorded. The same upper surface area of ASA plastic was in direct contact with the embers for 10 minutes. This process was repeated 3 times during that 10 minutes with 3 different ember samples. During that period, readings were consistently above 150 degrees, often above 250 degrees, and a peak temperature of 288 was observed. The plastic component was then inspected for damage. There was no permanent damage to the component, the surface temperature of the material did not reach ignition point, and no flames were observed. As step 3, a simulated ember attack was reconstructed. 12 embers, similar to those tested in steps 1 and 2, were loaded randomly into a container and dispersed onto a 30-degree pitch roof surface, allowing the embers to behave as if they had fallen and rolled down the roof. The smooth, solid surface of the Eaves water system profile caused more than 50% of the embers to be deflected directly to the ground. Only 7 of the embers remained in contact with the gutter and roof structure. The geometry of a roof will always cause embers to be concentrated towards the valley and away from the external corners. 5 embers came to rest on the upper surface of the valley gutter, and 2 embers came to rest on the gutter surface. The embers were observed for a period of 5 minutes, and while there was some light smoke, minor disfiguration to the top surface of the valley gutter cover, the materials did not reach ignition point and there were no flames. As step 4 of this test, hundreds of ember samples created using the same process as in previous tests were loaded into the same open gutter section. The temperature was measured and recorded, and again surface temperatures were consistently above 250 degrees Celsius. The upper surface of the gutter was covered in dry leaf litter, harvested from a 30-degree pitch roof under a white cedar tree. The quantity and density of leaf litter was a close reproduction of the source. Again, the smooth, solid surface of the Eaves water system profile caused a large percentage of the ember material to be deflected to the ground. However, due to the large number of embers used, many were now in direct contact with a typical fuel source. At 1 minute 45, first flames were visible. By 2 minutes, 3 flame sources were evident, and not surprisingly the largest of these was located at the valley gutter, where there was more fuel and more embers. The fuel burnt at a steady pace at 3 individual flame fronts for the next 3 minutes, and at approximately 4 minutes 45, there were no visible flames and the fuel had been expended. It was further noted that as a result of the high attach position and the fully enclosed profile, the fascia, which in this case was timber, was not exposed directly to flame. You're never going to get a big loading on an outside corner. It's only ever going to be on the valley. The outside corner is always going to look like that, which is why I didn't put too many leaves up that end, because they're always going to blow off and fall off on the corner.
Yep. Well, there's never going to be a lot of leaves on the corner.
The coals would sit there, and let's see if it eventually does any damage at all. But we'll have another couple of minutes, but I think it's pretty obvious that that's it. It's not going to do anything. The embers were left in place, in full contact with the roof, the gutter surface, and the plastic components. At 6 minutes 45, a full 5 minutes after the first flames, the remaining debris was removed and the damage assessed. Do you want to just then brush some off just in the end corner of the gutter? You can see what's happened underneath. There was no permanent damage to the roof, the gutter, or the plastic components, and no evidence of any of these having ignited and transitioned to a fuel source. So what temperature have you got there where the fire's just gone out?
65. Plastics, 84.
Now check the temperature of the roof up the top where the fire hasn't been at it.
31. .82 on the iron, 83 on the plastic. Stainless steel mesh, 64.
The chemical and mechanical properties of ASA plastic are well known, and the product has been tested many times to UL 94 standards, but this does not constitute bushfire testing. However, common sense conclusions can be drawn. Applying the physical properties of ASA and the fact that all components are 4 mm thick and fitted to the extremities of the structure, it is most likely that sustained ambient temperatures in excess of 250 degrees Celsius would cause the ASA components to melt and fall from the structure. On the average house, the total weight of ASA components is approximately 5 kilos and the surface area less than 1 square metre.